Welcome to this lecture on the role of determinants in matrix inverses. What we want to do over here is to see how finding out the determinants of a matrix helps us to check whether first of all it is invertible or not, and next to actually compute the inverse. So, previously we have seen how to define a determinant, how to compute a determinant, then we saw how we can look at different determinant properties which help in its evaluation, and here we are going to look at an application of the determinants in computing the matrix inverses. So, we are going to look at the role of determinants in matrix inverses. Now, one of the things is perhaps good to recall is what is a matrix inverse, why should we care about a matrix inverse, why should we care about inverses in general. So, if you recall the definition of a matrix inverse, it is that if you have a square matrix A, another square matrix B such that A times B, so the matrix multiplication of A and B both on the left and the right. So, AB is equal to BA is equal to the identity matrix. So, that is the definition of an inverse, and we denote the inverse of a matrix by A power minus 1. So, we have matrix inverse of a matrix A is defined by the expression A inverse equal to A inverse A is equal to identity, and this is the notation for inverse. Right. Now, what is the main idea here of an inverse? So, what is the idea of an inverse? So, let us forget about matrices, or let us look at a simpler 1 by 1 matrix which is nothing but a scalar. So, let us say the number 2. Why do we talk about the inverse of 2, or like do we talk about the inverse of 2, is it required? Well, we want to say, okay, if you have an expression or an equation like 2 times x equal to 1, how do we solve for x? For many of us it might be very straightforward, okay, 2x equal to 1 means x equal to half, but what is the underlying idea, how is it related to matrix inverse? So, let us look at that. So, if you have an equation like 2 times x equal to 1, and this 2, you can think about this as a 1 by 1 matrix or a scalar equivalently. How do we solve this? Is there an inverse of 2? There a way to find inverse of 2? Is it needed? Right. So, essentially what we say is that there is a notion of multiplicative inverse. That is, that if we multiply 2 by the number half, which is nothing but 2 power minus 1, then what we get is 1, which is in some sense the multiplicative identity. And so, effectively what we are doing in solving that equation is that we are multiplying both sides by a half, and then we are getting x is equal to half. So, we have 2x equal to 1. So, we multiply both sides by 2 power minus 1. So, that you get 2 minus 1 into 2 times x is 2 minus 1, and this we know from how we define division multiplication, that this is 1. So, that means that x is 2 power minus 1 or half. So, it is this notion of multiplicative inverse which, broadly speaking, we are expanding to the notion of a matrix inverse. Alright. So, this is broadly speaking what we are saying is we want to have an inverse, and why we would want a matrix inverse, because just like here we have 2 times x is equal to 1, we could have a general matrix equation which is A times x is equal to b, and here x is not just a scalar but a vector, and so is b, and then one way to solve it is to find the matrix inverse A inverse and multiply both sides and then get a solution for x. So, we have may be used for matrix equation. How? We may have a equation, consider an equation Ax equal to b. Now, this is a general n by n matrix. So, if we could find A inverse, then we would multiply on the through the left. So, we would say A inverse times Ax equal to b, which would give A inverse times A x equal to A inverse b, and then this is nothing but the identity, and identity times a vector x is just the x itself. So, this is A inverse b. So, this is why we would like to have a inverse of a matrix for trying to solve these matrix equations, and this is a direct generalization of this algebraic concept of finding what solution of a equation like 2x equal to 1 or 2x equal to 3, you multiply by the multiplicative inverse, which is half. Of course, we know that if we instead of 2, if we had the number 0, then it is very hard to solve the equation, because 0 times x equal to 1, what is the solution? And what we will see through this lecture, through this idea of determinants, which by now must have come through how important this is, that if we now look at the determinant of the matrix A, that holds the key in trying to get, okay, what is the invertibility, does it exist, does the inverse exist, how do we calculate the inverse. So, that is what we want to do in this lecture. So, we want to show that if you have a determinant of a matrix being non-zero, then the inverse exists, and how we can define the inverse of a matrix using the determinant and another quantity which we should define shortly. So, that is the goal of the lecture, and but the idea is very simple, is that we are looking for a way to get a condition to try to see how we could then solve matrix equations, how we could solve other problems of this nature. So, that is the goal of the lecture. Okay. So, goal is to show the use of determinants in checking for invertibility of a matrix. So, that is the one thing, and to actually compute it, right. So, let us begin. Now, how do we come up with a general matrix, let us say a 3 by 3 matrix, more generally an n by n matrix? How do we come up with the inverse of the matrix? So, the idea here is going to be a combination of the definition of a determinant and also one of the properties that we looked at, specifically that the determinant is a sum of the product of elements of a row or a column and their corresponding cofactors. So, that is a determinant, and if you look at the cofactors of another row or column, then that sum goes to 0. So, essentially this idea that something is a determinant and something goes to 0, we are going to exploit that, the use of these cofactors in forming a general inverse of a matrix. think the ideal place to start over here would be to start with a 3 by 3 matrix and look at the columns. Okay, so let us look at a 3 by 3 matrix. Consider a 3 by 3 matrix what in general situation we have used A11, A12, A13, A21, A22, A23 and A31, A32, A33. All right. Now, the idea is that if we denote Aij as the cofactor of the element Aij, where I and j are the indices for rows and columns respectively. What we want to do here is to define the idea of an adjoint of a matrix, which is the matrix associated by taking the transpose of a matrix where each element is replaced by their corresponding cofactors. So, let me write it down and I will say it again. So, we will define adjoint of this matrix as the transpose of a matrix obtained by replacing each element A with their corresponding cofactors. So, A11, A12, A13, A21, A22, A23, A31, A32, A33. So, the adjoint is of a matrix is obtained by taking transpose of matrix where each element is replaced by its cofactor. All right. So, the adjoint of a matrix is defined by the transpose of a matrix obtained by replacing each element by the corresponding cofactor. So, in this case, in this 3 by 3 case, we have the matrix A11, A12, A13, A21, second row first column, second row second column, second row third column, third row first column, third row second column, third row third column. Okay. And so, this is the matrix and its adjoint is obtained as the matrix where each element is replaced by its cofactor, and A12 is replaced, but by taking the transpose it will come over here, and A13. Same here would be A21 because we are replacing the element here with the cofactor and then taking the transpose, and then A22, A23. Same over here, this would be A31, A32 and then A33. All right. So, this is the adjoint. So, if you call this a matrix A, then this will be denoted by adjoint of A. All right. So, here is a matrix, here is adjoint. Now, to understand the idea behind coming up with this adjoint, let us just calculate some terms of their matrix product. All right. And this will be using these properties of what happens when you multiply the row when you sum the product of a rows with the cofactors of a different row, right. So, let us take a look at this. So, what would be the matrix associated by, what would be the first term in this matrix product? This would be A11 times A11 plus A12 times capital A12 plus A13 times capital A13, right. So, this expression you can realize is just the definition of a determinant, okay. And in fact, we could replace this by the determinant. So, this is nothing but the determinant of A. What about the second column? What about the second entry over here? So, this would be the first row multiplied by the second column. So, it is going to be A11 A21 plus A12 A22 plus A13 A23. So, if we look at it, this expression is nothing but a sum of a product of elements of the first row of the matrix with the cofactors of the second row, and which we have seen in the properties evaluates to 0, right. So, this is 0. Now, there is going to be one more term, but for reasons of space I will not be able to write it here, but let us just evaluate one more term and let that be the term in the product which is in the second row and the first column. So, let us evaluate this term here. What is that going to be? That is going to be the second row multiplied by the first column of the adjoint. So, this will be A21 A11 plus A22 A12 plus A23 A13. So, if we look at this term, what is it going to be? This is the sum of product of elements of the second row with the cofactors of the first row. So, this will also, as per the property, evaluate to 0, right. Now, we could do a fourth sum, we could do all of them, but the general idea, and this I encourage you to verify, is that all the diagonal elements will be nothing but the determinant, and all the off diagonal elements are going to be zeros. So, the final answer over here, and this we can do not just for a 3 by 3 matrix, but for an n by n matrix in general, is that we will get here. So, this is a 3 by 3 matrix, this is a 3 by 3 matrix, this product will also be a 3 by 3 matrix with only diagonal entries, which is coming from here, a 0 which is coming from here, another 0 which I encourage you to check, this 0 comes from here, this is also going to be a determinant of A, 0 0 0, determinant of A, and this is going to be determinant of A. So, this is a 3 by 3 matrix, right. So, this will be determinant of A times an identity matrix. The first time let me write down 3 by 3, but in general we can understand from the context what is the dimension of the identity. So, there it is. So, we have a matrix and we have multiplied it by its adjoint, which we have defined here, and the reason for defining the adjoint in this way is to be able to see this idea that only the diagonal terms are determinant, off diagonal terms are 0. So, we can write it down as a constant, and in this case it is this all important determinant which is the constant times the identity matrix. And why is this important? Well, this is important because in looking for a matrix inverse, we are looking for something to multiply the matrix by such that it is equal to identity. So, here we have not got an equal to part, but we have got something which is proportional to an identity, and so we can, but by using this we can define that matrix which when multiplied by a square matrix will give you identity. And what will that matrix be? That will be nothing but the adjoint of A divided by the determinant of A. So, the statement that we want to make, or the equation that we want to write, is that A times adjoint of A This we found to be equal to determinant of A times identity, and you can also check that if we now, instead of post multiplying adjoint of A, if we say adjoint of A times A, that will also come as determinant of A times identity, and combining these equations we can write that A times the adjoint of A is equal to adjoint of A times A will be equal to determinant of A times I. So, here A is a 3 by 3 matrix, adjoint of A is a 3 by 3 matrix, this is a scalar, this is a 3 by 3 matrix, or in other words we can say A times adjoint of A divided by determinant of A is equal to adjoint of A by determinant of A times A equal to I, and this we can write down when the determinant is not 0, right. And if we compare with A inverse equal to A inverse A equal to identity, which is the defining equation for an inverse, we can get that A inverse is equal to adjoint of A by the determinant of A when determinant of A is not 0. So, this is how we can compute the inverse of a square matrix with a non-zero determinant. That is just that you define an adjoint of A, which is nothing but the transpose of a matrix obtained by replacing each element with their corresponding cofactors, right. And if you divide that by the determinant of A, then through a generalization of what we have just seen, we can come up with this relation between the adjoint, determinant and the inverse. So, here is this important number of determinant which is now playing a role in defining the inverse of a matrix, which is important for the reasons that we outlined at the beginning. Okay. So, this is what we want to say in terms of how to get the inverse. Next we will look at some more ideas behind the inverse of the matrix and how the determinant plays an important role, and including specifically saying how we can say, like here we are saying that okay, if the determinant is not 0, that is when we can define the inverse. Next we will say that okay, we can make that even more stronger statement. Okay. But before we do that, I think it is important to point out over here that this adjoint is also a matrix. In fact, it is a matrix of the same order as the initial matrix. And that being said, what can we say about the determinant of this adjoint? Does that make sense? So, a natural question which arises now that when we look at matrices is what is their determinant, and can we from this come up with a determinant of the adjoint? That is what we want to look at now. So, a note here is what is the determinant of the adjoint, right. So, what is the determinant of the adjoint? And in answering this question, we have to state a property which also has independent use, independent importance, and that is that a determinant of a product of two square matrices is going to be the product of their respective determinants. The property that we use the property that determinant of A into B is equal to determinant of A times determinant of B, right, where A and B are square matrices. Using some simple examples, you can verify that this is the case. We will not go into a proof of this property here, but we can just check whether it is the case. You know, it on surface it might look like a simple property, but it is not always the case. For example, if you have the sum of two matrices, it is not necessary for the determinant to the sum of their determinants to equal to that value, but in this case of the product it happens. So, it is in fact a remarkable property, and just to see how it works out, let us look at some examples. So, for example, if we take suppose you take the matrix A as 1 2 2 1, what is its determinant? Is 1 minus 4, so minus 3, and let us say we have another square matrix B which is 2 1 1 2, what is the determinant? Is 4 minus 1 3. What about their product AB? This is 2 2 4, 1 2 5, 2 5 and 4. So, the determinant is 4 16 minus 25, so minus 9, which is equal to, so these are the determinants. So, this is an example of saying that, therefore, we can check the determinant of AB is determinant of A times the determinant of B. Okay. So, we are going to use this property to find out this adjoint determinant of the adjoint, and going back to the definition of the inverse and the situation that we derived, that is where we are going to apply this property, okay, that the determinant of a product, because we have just seen that the product of A and adjoint of A is equal to determinant of A times I, right. And so, now we are going to take the determinant of both sides, and because we can decompose the determinant of a product of matrices into the product of their determinants, that is how we are going to get this idea. So, first in the 3 by 3 case that we were looking at, we use the property in here. So, when we have the fact that A times adjoint of A equal to determinant of A times the identity, right. So, take the determinant over here, and the fact that we had the determinant of A times adjoint of A is going to be the determinant of A, remember, is just a scalar, right, times an identity. So, in the 3 by 3 case, the right hand side is going to be just determinant of A cube, right, because this matrix is nothing but the diagonal matrix with the determinant of A in the diagonals 3 times. So, determinant of A cube, this is for 3 by 3 case, and in general it is going to be determinant of A power n for n by n case. And what about the left hand side? Well, using the property that the determinant of a product of matrices is the product of the determinants, we will get the determinant of A times the determinant of adjoint of A, right. So, if the determinant is not 0, then we can write, just cancel one determinant of A on both sides, that we can get that the determinant of adjoint of A is equal to the determinant of A whole square for the case of 3 by 3, and in general it is just determinant of A power n minus 1 for n by n. So, we have introduced a new matrix which is the adjoint of A, and immediately, because we are talking about determinants, it is natural to ask what is the determinant of the matrix, and here we see that the determinant of the adjoint is related to the determinant of A, it is n minus 1. Okay. So, this is the adjoint determinant, and just thinking about it, like if n is equal to 3, then it reduces to what we have seen. If n equal to 2, it is determinant itself. For n equal to 1, it is 1, and I think that is just a problematic case or a special case which comes out because for a 1 by 1 determinant which is a scalar, it is really hard to define a cofactor. So, I think this sort of expression should be taken for n greater than 1. Okay. So, this is the determinant of an adjoint of the matrix. All right. So, now that we have seen that we are trying to find out about the inverses and determinants and adjoints, and this is the new matrix that we defined in terms of the adjoint, and now we can look at how we proceed from here in terms of noting this importance of a determinant in trying to find out the inverse of a matrix. Now, we just state the same things in a more formal fashion. So, in many places we have said that the determinant of A is not 0. So, note determinant of A not 0 condition invoked or used many times in this lecture. So, based on this we can define a singular matrix as, so this is a new matrix, new word that we are using here. We are defining a singular matrix as a matrix with a 0 determinant and analogously we are going to define a non-singular matrix. What is going to be a non-singular matrix? A non-singular matrix as a matrix with a non-zero determinant. So, a singular matrix will be one with a 0 determinant, and a non-singular matrix will be one with a non-zero determinant. So, in a sense we are sort of highlighting the importance of the determinants in defining classes of matrices as either being singular or non-singular depending on whether their respective determinants are 0 or not 0. Okay. And the theorem that we want to state over here is that a square matrix A or A is invertible if and only if it is non-singular. So, let me write down that statement and then we can look at the proof. So, we are going to say that the theorem is a square matrix A is invertible if and only if A is non-singular, meaning that it has a non-zero determinant. How will we look at the proof? Well, we will look at both ways, both the if and only if part. First we will say that if A is invertible, then it is non-singular, that is its determinant is non-zero, and the other way around, that if it is a non-singular matrix, then we can show that A is invertible. So, let us look at this part first. So, if A is invertible, that means that there exists a matrix B such that A times B is equal to B times A equal to identity. And now taking determinants, taking the determinant, we can get that determinant of A B is equal to determinant of identity. So, what is the determinant of the product of matrices? It is nothing but determinant of A times the determinant of B. And what is the determinant of identity? Identity is a diagonal matrix, each element is 1, and so this is equal to 1. Now, this already says that determinant of A is not 0. Why? Because if it was 0, then this relation would not hold, and we are guaranteed this relation holds by these sequence of steps which start with the fact that A is invertible. So, this means just by the definition that A is non-singular, right. So, the implication part is just by defining or by starting from the fact that A is invertible, using just a series of steps including the definition of this invertibility, including the fact that you can take the determinant of a product of matrices, nothing but the product of the respective determinants, we can say that A is a matrix which is non-singular. The only if part is also relatively simple. It says, okay, if we know it is non-singular, it means that we can define a matrix like the adjoint of A divided by the determinant, and that is where we are using the fact that determinant is not 0, that we can divide by the determinant, and this, as we have seen specifically for the 3 by 3 case, but we can check for a general n by n case, will define the inverse of the matrix. So, the inverse part or the reverse part is that A is non-singular. This means by definition determinant of A is not 0, which means we can define A inverse is the adjoint of A divided by the determinant of A, and this, as we have seen, satisfies the properties of what is required from the matrix inverse, and therefore A is invertible. This satisfies A inverse equal to A inverse A equal to I, therefore A is invertible. So, the statement here was that A is invertible if and only if it is non-singular, and non-singular is defined in terms of the determinant. So, there you have it. So, you have or we have a way in which we say that, okay, if by calculating the determinant of a matrix, if it is non-zero, then you are guaranteed that it is invertible, and not only that, that is just the statement, and in the proof we have come up with a way of defining the inverse. So, this theorem is significant for these two reasons, that it both gives a condition for checking the inverse of a matrix, which is the non-zeroness of the determinant, and also it defines the inverse. All right. So, this can be summarized in this statement, that determinants help in checking invertibility of matrices and also in computing the inverse. So, this is the significance of the last theorem. Significance of theorem. So, determinants are important. Okay. So, that is how we have seen how determinants help in finding out the invertibility of matrices and in computing the inverse. Now, we are going to look at some examples of calculations of the inverses and how we can, of course, it is not always the case that just because we know now we can define an inverse in this adjoint matrix and using the determinant, we can also come up with by sometimes in some cases ultimately it is a question of which is the easier way to define the inverse. So, if it is a general case, we can always use the adjoint definition, divide by the determinant, that will be the inverse. In some other cases, if for example it is a purely diagonal matrix, we can just by inspection also come up with an inverse, because ultimately the concept is that if you take a matrix, multiply it by its inverse, that should give you identity. So, whichever way you can come up with, but the importance of determinants is that it gives some method to this intuition, that you can formally come up, define an adjoint, divide by the determinant, and that will give you the inverse, right. So, let us look at some examples. So, one example is as follows. Let us look at a 3 by 3 matrix. Consider a matrix like x 0 0 0 y 0 0 0 z. Now, looking at this matrix, it is a diagonal matrix. So, what would we multiply a diagonal matrix by so that it gives you identity? Then we could go through defining the adjoint of this matrix, finding the determinant. Let us do that. Another way, we could also directly write down the solution. What would be the direct solution? Well, just by looking at this, we see that, okay, if we can multiply just each of the diagonal elements by their respective inverses. So, if I can multiply x with 1 by x, y with 1 by y and z by 1 by z, and that will only work if each of them is not 0, then it is possible I can get an identity. And how will I do that? Well, I can do that if I have another diagonal matrix which entries 1 by x, 1 by y, 1 by z. So, what I am saying is that one way to do it would be to say, okay, if I multiply it by, so this Roman numeral 1 is not identity, so maybe I can just say that this is 1. So, if I multiply by 1 by x 0 0 0 1 by y 0 0 0 1 by z, we can verify that this product of this matrix and this product is going to be identity, because x 0 0 multiplied by this first column, x times 1 by x is 1 0 0. Same if I multiply this by this diagonal matrix, there is no term which is not 0. Same with other columns, essentially only the diagonal terms will be picked up. But this will work, this works when x is not equal to 0, y not equal to 0, z not equal to 0. Right. So, this is one inspection way. So, this might work for some cases, like there is nothing, there is no requirement that always a matrix inverse have to be defined through the adjoint route. Sometimes by intuition we can always come up with a thing, but the importance of what we have done now is that it gives a formal way to come up with the inverse. So, let us try to define the adjoint of this matrix, come up with the inverse in the way we have defined it, right. So, first of all, what we will do is we will check, okay, is it invertible at all? For that, how do we know? Well, the theorem says if and only if the matrix is invertible, if and only if the determinant is 0, excuse me, if and only if the determinant is 0. So, what is the determinant of this matrix? So, this is the second way. So, 2, method 2. What is the determinant? Determinant is, it's a diagonal matrix. So, by the property the determinant is x, y, z, and this is non-singular if determinant is not 0. So, x, y, z, the product is not 0, and that you can see is the same condition as we see over here, that each of these are non-zero, then it is not 0, and vice versa. So, these are the same condition that we get. So, already we see that this can be it is going to be an equivalent kind of derivation. Well, what about the adjoint? Can we come up with an adjoint of this matrix? So, it is going to be transpose of the matrix obtained by replacing each element with their cofactor. So, what is the cofactor of this? It is the determinant of this matrix. So, that is y times z. What about here? Well, you see, if you just black out this row and this column, you are left with a matrix which has 3 zeros, in fact one row identically of 0, and so that is going to be 0. Same over here. So, for example, if you black out this column and this row, all we are left with is these 4 elements. A number of ways to use the property to say that the determinant of this thing is 0. One is that one row is 0, second is the upper triangular matrix with the diagonal elements are 0. There are many ways, or you can also directly calculate the determinant. In fact, if you look at all the calculations, you see that all these terms will be 0. This will be x times z, and this will be x times y. It is a diagonal matrix, so the transpose is equal to itself. So, this is, just to write it down again, would be y z, x z, x y, and everything else is 0. Okay. And the inverse, which will be the adjoint divided by the determinant, okay, that expression, you see that we divide y z by x y z. So, you will get 1 by x. So, that is nothing but what you got here. You divide x z by x y z, we will get 1 over y, which is this element. You divide x y by x y z, we will get 1 over z. So, this term which we derive from this more formal method will going to give you the same thing. So, both through formally defining the determinant and also by inspection we will come up with the same sort of method. So, this the purpose of the example is just to say, okay, it is not that this is some magical way to come up with determinant? Well, there is some magic involved in how we define the adjoint, how we come up, how someone came up with the idea of coming up with an adjoint, defining the adjoint and so on, but ultimately the method is such that it matches what we expect. So, therefore, we should have confidence after having understood this example that yes, defining the inverse by the taking the adjoint and dividing it by the determinant, that should work. Okay. So, let us look at one more example of this, and just to solidify or concretify our understanding of how we can calculate matrix determinants. So, in this let us look at a 2 by 2 example, and let us look at a numerical example here. So, let us look at an example A, which is 2 1 3 2. So, maybe let us have different parts over here. We can say calculate A inverse. Okay. So, looking at this matrix, now this is an example of having a matrix. Just by inspection it is hard to come up with an inverse. Of course, for a general 2 by 2 matrix we can develop a formula and come up with the inverse, that is also fine, but let us do it in the structured way. For this, the first thing always before doing the calculation of the inverse is we should check whether it is existing or not. So, the first question to ask is, does the inverse exist? Does inverse exist? How will we check that? Well, we will first look at the determinant. What is the determinant of A? Is 2 2 4 minus 3, 4 minus 3 is 1. So, the inverse exists as determinant is not 0. All right. Okay. Then next, so we know the inverse exists. Next, how do we calculate it? Well, we can calculate it by defining the adjoint. In fact, here the inverse is equal to the adjoint. Why? Because the determinant is 1. So, what is the adjoint? So, then what is A inverse? So, A inverse would be the adjoint of A, which is that as determinant of A is 1. What is the adjoint? So, adjoint is again the, so let me write it here perhaps, that is the transpose of a matrix obtained by replacing each element with the cofactor. So, cofactor of 2 is 2, cofactor of 3 is minus 1, cofactor of 1 minus 3, minus is coming because it is in the second row first column. So, minus 1 power 3, and then if you delete this column and this row we get 3, same here. So, this is 2 minus 3 minus 1 and 2. And now we can check. So, we have 2 3 1 2 and 2 minus 3 minus 1 2, determinant is 1. So, this is what the what we have studied in this lecture is the inverse of the matrix. Is it the case? So, it is always good to check the two. So, let us check, let us at least check whether A times A inverse is the identity. So, let us check. So, what is A times A inverse? So, this times this. So, the first element is 2 times 2 plus 3 times minus 1. So, that is 1. Second is 2 times minus 3 plus 3 times 2. So, minus 6 plus 6, that is 0. This entry is 1 times 2 plus 2 times minus 1 is 0. And the last entry is 1 2 times minus 3 times 2. So, 4 minus 3, again that is 1. So, which is exactly like the identity. All right. So, this is completes what we want to do, is that we wanted to calculate the A inverse of something which not directly we can say is the inverse. So, what is the inverse? But maybe for a 2 by 2 you can come up with formulas. In general it is hard, but this is the way we can calculate the inverse for a general matrix. One of the things also is important to mention is that there are different ways to calculate the inverse. In some sense the determinant plays an important role in most of them, but there are other ways. So, for example, how do we calculate the inverse? So, calculating inverses, right. So, what are the ways? So, the ones that we have seen is by inspection, and that happens in some cases. So, by inspection for example, for some cases. Then there is using this definition of the adjoint and the determinant, which has a plus point that it also gives you whether we should calculate the adjoint or not just by checking that the determinant is 0. It gives you a condition for the existence of the inverse. So, by using determinant and adjoint. So, the bonus here is that provides a condition to check for existence of an inverse. There are perhaps other ways also, and just to complete this subject, just wanted to present a simple example for this, and that is that if you have a matrix A which satisfies a polynomial equation, in some cases that can also be used to calculate the inverse. So, in particularly for the example that we just presented, for previous example, if we continue the previous example, the matrix A, which is defined to be 2, 3, 1, 2, that can also be shown to satisfy the equation satisfies A square minus 4A plus I equal to 0. So, you could check this, you can say A times A plus I whether it is equal to minus 4A or not. So, this can be checked. How can this be used to calculate the inverse? Well, consider multiplying. How to use this to calculate A inverse? Well, we can multiply by A inverse, then we will get an equation like A inverse times AA. So, I have replaced A square with A times A minus 4 A inverse A. So, I just taken this 4 outside plus A inverse times I. So, this is 0. So, one of these can be combined. A inverse times A is identity. So, this is identity times A, this is again identity. So, minus 4I plus A inverse, because identity times any matrix is the matrix itself, or this is A inverse is equal to 4I minus A. So, let us see whether this gives you the inverse. So, 4I will just have 4 0 0 4 minus A, and A is written here. So, this will be 2 minus 3 minus 1 and 2, and this we can check from what we were doing before, that this 2 minus 3 minus 1 2 is the same as what we have got here. So, this there is not just one way to calculate the inverse, this is also A inverse. So, another way to calculate A inverse, right. So, just for completeness I show this because the reason I showed this was just because there are different ways to come up with the inverse. One is that you have by inspection, by calculating the adjoint and the determinant, and this is a way in which there may be other ways. So, just determinants are important, but of course, they are not the only way to calculate the inverse. And while we are at it, I mean, one question which might arise is, okay, where is this kind of equation coming from? Surprisingly, or perhaps not surprisingly, because determinants are very important, these equations come from looking at the determinants of some special kind of matrices. So, this one you can check, this equation is the determinant of a matrix obtained by doing the following. So, lambda I minus A, or determinant of lambda I, so lambda minus 2. So, lambda here is a variable, equation is lambda minus 2 minus 3 minus 1 lambda minus 2. So, and if you put lambda equal to A, then we will get this equation. So, this can be checked. This is not directly related to the idea of how determinants help in getting the matrices, but what we can check in state in general is that if we have any square matrix A and construct the matrix lambda I minus A, take the determinant and then replace lambda with A, and whatever 1 is there you can replace for identity, then we will find that that equation that is satisfied by the matrix. So, if you replace lambda, then that equation obtained in this fashion, which also includes a determinant, can be solvable by the matrix, and then that fact is also used in some other equations. So, that is a more of an advanced topic, which is to see some other properties of matrices, but my main intention of presenting it over here is that, okay, there may be other ways, but there also these determinants are important. So, the determinant is an important tool, an important number associated with a square matrix, many interesting properties. There are some geometric ideas, some algebraic ideas, there are very interesting properties of the determinant itself. Some we have presented here, for example, the product of the determinant is the determinant of the product, that idea. It has many applications, one of which we have seen here is in terms of finding out the inverse of a matrix, and specifically what we have, the statement that we have made is that determinants help in checking the invertibility of matrices and in computing the inverse, and this was the significance of the theorem that we presented. All right. So, with that I end this lecture and I thank you for your attention. Thank you.